You're gonna have to do it again.
No problem.
Yeah, we usually start 5 minutes later, so. Have we started? Oh, you started.
Yeah, we start. We can start.
Oh, okay, we're already being recorded, so you know what should be said.
This is before.
But the sound is working, so. Alright, tell me state secrets.
Okay, thank you all for being here. Today we had the pleasure of introducing Pedro Figueira. For those who don't know Pedro, he has recently started working here at IAA since October this year as a postdoc. Pedro was a PhD student of Michel Mayor and Francesco Pepe in the University of Geneva. He graduated his PhD there. And for a long time, he was a staff astronomer and instrument scientist for ESPRESSO in Chile at ISO. He has been at the Observatory of Geneva in the meantime. After his stay in Chile, he has been in the Observatory of Geneva managing the Euler telescope and doing other research there with the radial velocity team. And now he's with us here at the Institute under the Thirsty project that I am behind. So happy to introduce you, Pedro. He's going to present the state of the art on the instrument ESPRESSO and some latest results that are really promising for the search for Earth analogs around solar-like stars. So let's take it out. Thank you.
Thank you, Rafa. Thank you, Thea and Alvaro, for this very nice invitation. It's my pleasure to present you my work after moving from Geneva, and I will try to frame it showing, as Rafa said, the state of the art, but also for people that don't necessarily do radial velocities, because there are other things that are very interesting in this world, right? But if we look at the story of radial velocities and detecting planets with radial velocities, it's interesting to look at the family album of Geneva. By the way, Michel Mayer's anniversary was yesterday. So if we look at the progression of radial velocities, we started with this instrument called LOD that went online in 1993 in France and allowed us to detect the first exoplanets. Here you see the radial velocity as a function of phase for an orbit of 3 days. The planet 51 PEG-B detected with LOD, and this was just the first planet around a star like our own, and this was the first spectrograph that was able to do so. But then in the family, others appeared. The sister of LOD is Coralie, and observes on the southern hemisphere. And then there were other instruments such as HARPS and HARPS Nord. And in 20 years, we went from the ability to detect stars orbiting around other stars in radial velocity to the ability of hopefully detecting a planet like our own. And even though this was this idea of detecting a planet through radial velocities motivated the development of instrumentation, there was a research topic that piggybacked on exoplanets and on radial velocities, which was the detection of atmospheres that started in 2010, which was something also groundbreaking. But if we come back to radial velocities and spectrographs for radial velocities, the question is, how are these different? A spectrograph is a spectrograph, right? So what makes a spectrograph for exoplanets and for precise radial velocities for exoplanets different? Well, there are basically 3 things. The first is that at the entrance of the spectrograph, there is a fiber that intends to capture the light and to scramble it to make it as uniform as possible as it enters the spectrograph. And we see that circular fibers scramble the light very well in azimuth angle, but not in radial direction. You can still see some effects. And if the star moves around or enters or leaves the fiber, these things will change. This light distribution will change, which is a problem. And that prompted the creation of octagonal fibers. And octagonal fibers are like an octagon. And since they have this funny shape, the way that light reflects inside a very long octagon, it actually scrambles the light much better because the reflection of light is more chaotic inside. So in the end, you have something that is very, very homogeneous. And then you feed it into a spectrograph. And the spectrograph is different also because it is fixed and stable. It is designed, put into a vacuum vessel, closed with a key, and no one opens it. No one touches it. There is this joke that the one harps in La Silla. There is one person who has the key to harps, is Gasparello Curto, and he wears the key on his neck, you know, like a wedding ring or something like that. And no one enters the room of the spectrograph even. The spectrograph is completely fixed, completely stabilized in pressure and in temperature, because the pressure and temperature change the refractive index of the air and change the projection of the light on the CCD. So this is the second point. And then the third point is that even though we do our very best to minimize the changes of spectral line shapes and the changes of line positions by these parasite effects, we still need to monitor them in real time. So we have a spectrograph that not only has interference orders from the star, but it has a second set of interference orders that you see here that is put in between and that you use to inject light from calibration lamps. Here you see the light coming from the star, and here you see the light coming from the lamp. So if the light from the star changes in position relative to the light from the lamp, then you measure a real-time variation of radial velocity that is a parasite that you can remove in real time as well. So these are the three things that make the spectrographs for radial velocities a bit different. And if you want to increase the precision, what do you do? Like from very simple principles, you just want the flux to be as high as possible. So you want a big telescope, the wavelength domain to be as wide as possible, so that you get as many lines as you can. And then you want the resolution to be as high as possible, so that you have very sharp lines. And of course, we cannot forget that not only we need the spectrographs to work well, but to work for long and with in a very dedicated way. Today we follow stars, or as of today, we can follow stars for longer than 10 years. And that's remarkable to have operations and observations on the same star for very long time spans, and also at very specific phases of the planets. The other day, Rafa was telling me how difficult it is to plan the observations with GWST to catch the transits, and here is similar. We want to catch the planets around the star on very specific phases, and that also requires time and requires teams. And I would like to remind you that there is a large group of very happy people working for you at ESO and in many other observatories, and they are the unsung heroes of these papers that we write. And I had the pleasure of working with them. I had the pleasure of working with them as a staff astronomer and working with ESPRESSO. ESPRESSO was designed to measure radial velocities in such a way that we can detect planets like our own around the star like our own. This requires 10 centimeters per second of precision, because that's the signal that the Earth imprints on the sun. And that's very difficult. This is ESPRESSO when it was being assembled in Geneva. And ESPRESSO is this viewer that you see here. And it's also all this paraphernalia that allows to connect ESPRESSO to the different telescopes. So these are the 4 unit telescopes, the UTs of Paranal, and the light is basically reflected from the telescopes into this room where there is ESPRESSO, and it goes through these black boxes that contain optical elements called ADCs and enters through the ADC in the spectrograph. So it's a very big facility. It's dozens of meters wide, fed by telescopes that are 10 meters, order of magnitude 8.2 to be precise. So this instrument went online in 2018, and the GTO, the work is.
Can I interrupt?
Sure.
Do you mean that the light is coming from the four telescopes at the same time, or can it be coming from one?
That is a very good question. Thank you. So the light can, the short answer is both are possible. So the light can be transferred through this set of optical elements called the Coude train, and it can be sent from the optical elements through here, reflecting, entering into one of the black boxes and then into the spectrograph, or from the 4 telescopes into the 4 black boxes, and then here there is an element that allows you to fuse the light, or to be precise, to fuse the 4 fibers. The problem is that as you do this, you lose resolution because you put these 4 fibers into a big fiber. So you blur the image of the star in the sky. So you lose resolution. As a consequence, when we search for planets, we use one of the 4 telescopes, highest resolution. And when we want to observe, for instance, transits, we can put the 4 together and we lose a bit of resolution, but we get more light. And that's how the observation of some of the faintest stars with transit was attempted, like the one, what's this? The TRAPPIST. TRAPPIST was observed with this setup. But for most of our observations, what we did was that we used either of the telescopes, the telescope that was available, to try to detect a planet like our own, with the highest resolution, with the highest precision. And the GTO, so when you deliver an instrument to ESO, you basically invest millions of euros into that thing, and ESO doesn't pay you back in money, it pays you in how to say, in equivalent money, which is telescope nights. So ESPRESSO cost, I think, order of magnitude, I think it was 10 million or 20 million if you put the personnel. And then ESO gave back 270 nights. 270 nights UT. If you use 4 UTs, you use 4 nights at once. And yes, I think we were, how is it, shortchanged. And so what we did is that basically we split those nights into different signs. And one of the signs is to search for planets like our own, around stars like our own, in a blind way. You look at the star, you look at the best stars, and you try to find if there are planets there. There were other studies like atmospheric studies trying to study transits and atmospheric transmission, or to confirm transiting planets, and even constant variations and other science. But what I'm going to talk about is this search for planets like our own. I was the manager of this working group from the GTO, and I was also the instrument scientist, which is the person that receives the instrument at ESO. So I didn't sleep much for 3 years. And in the ESPRESSO GTO, the first result that came out, and it was very interesting, was Proxima b analysis. So Proxima b had been detected before, but with ESPRESSO, there was this interest of actually remeasuring it to compare it with HARPS. So here, transparent, you see the points gathered with HARPS that allow the detection of the planets. And the foreground points are the points with ESPRESSO. And you see that basically you can, with only 63 points, we can do what was done with 200 and something points with HARPS, because the telescope is so much larger. So it allows you to reach a much better precision on this type of stuff. Also, very interestingly, of course, we wanted to confirm the planet because that was interesting, and we wanted to confirm that the instrument was working well, but then we continued observing. And João Faria in 2022 took the analysis further, and he detected a candidate super-Earth around this star, another planet, with a radial velocity amplitude of only 40 centimeters per second. How was this done? By observing the star, the radial velocities as a function of time. As you see, this is much more complicated than 51 peg. There are many more signals because there is a strong contribution of the activity. The full weighted half maximum here, spectral indicator, activity indicator, tracks very well these variations, which are variations of activity of the star. And when you subtract this from that one, you can detect this planet and you can reach basically 40 centimeters per second. So as the GTO ended, we heard the whip crack of publish time. And I wanted to also to publish some work, of course. I wanted to, on top of doing these studies on specific stars, I wanted to do a comparative study to try to understand what we do understand and what we don't understand. And this is the paper I published last year, and I will explain to you a little bit the things that we learned with ESPRESSO. And feel free to ask questions anytime. So the first thing that we realize is that the 8.2 meter instrument telescopes are collecting the light very well, and it's impressive to see the photon noise as a function of signal to noise ratio. These were points taken from the different stars. This looks like it was created by a simulation or something like that. No, it's just that we can reach a precision of 10 centimeters per second, formal precision, noise uncertainty on the observations like this. That was impressive. But then when we start to compare the photon noise, the formal precision, with what we measure within a night, the scatter within a night, we see that there is a huge difference. The photon noise follows these very beautiful distributions around 10, 14, 15 centimeters per second, but within a night, you see these signals that are already at 40 to 60 centimeters per second. So it's time to take a break and remember what are the four things that we can see in a star when we search for radial velocities, for planets. The four things we didn't want to see and we find before planets. The first is the signal of pulsations. As the star pulsates, the outer layers of the star change their position, and we have an effect in spectroscopy. The line's position and shape changes as well. And this creates a radial velocity signal. And then we see also the effect of what we call granulation. Granulation is this umbrella term. It's a name for something we don't understand very well. And it's basically the observable signature of convection. And you have a star like our sun, the only star that we understand, maybe. And we see that we have the outer region of the sun, the corona, that has all these fluctuations in flux. But below, we have a convective zone and the photosphere, where you see also fluctuations here. And these fluctuations are fluctuations in brightness, but also fluctuations in radial velocity, if you point a spectrograph to them. And this creates a signal that we call the signal of granulation. It's just because, well, on the pulsation, you see that it's a star that expands and contracts. So as a toy model, it's easy to understand. The star expands and contracts. This creates a radial velocity signal because the outer layers of the star are approaching you or moving away from you. In the granulation, these bright and dark spots are just cellulose that go up and down like a heating, boiling liquid. And as they come up, they are hotter and they have different spectra that as they go down. So this turbulent movement has a radial velocity signal of its own. And then when several of these bubbles get together, you see a larger scale movement with a longer time scale that some people call supergranulation. But it's basically the ensemble of the bubbles that go up and down on a different time scale. And we can actually see this on some stars. This is on a giant star. If you kind of squint, you can see the effect of this in interferometry on some stars. And this has a radial velocity signal as well. Then, as the star rotates with spots, what the spot is doing is that it's creating a periodic signal with the period of the rotation. The star rotates like this. So as the spot fixed on the star moves relative to us, first it's hiding the blue rotating side, and then it's hiding the red rotating side. So it introduces a deformation on the lines because it's actually removing contribution from the star. If it removes contribution from one line of the rotating star, the average spectral line swings to the other, and vice versa. And this introduces a signal with a period comparable to our rotation. And then over the long term, many years, we start to see the magnetic evolution of the star. And here we see it on the sun. Over 10 years, we see that the sun basically had a very different average level of activity. And that is also seen on the 0 point of the radial velocity. It's like a very long-term signal that you add on top of everything else. But this is very hard to understand. And it's extremely difficult to characterize because to represent this by an average value, it's horrendous, as you can see. Look at this. There's all this going on, but okay, but the least that we can do is to represent this as an average value that changes very slowly with the time scale of the magnetic cycle. So these are the 4 things.
Pedro,
Yes.
Can I do a question?
Sure.
Yeah, thank you very much. So these 3, the pulsations, the rotations, and the magnetic fields can be considered like a temporal evolution.
Yes.
And the granulation is something like white noise, or it also has a temporal evolution that you can measure.
That is, yes. So this can be considered as a temporal evolution, and you are stressing that because we know well the time scales, right? Pulsation, we know the time scales from the modes of pulsation. These are very well defined by the instrument, the musical instrument that is the star, by the resonant chamber. The rotational scales, it's defined by rotational periods. And the long term, actually we don't know so well, but we know that on the sun is 11 years or 22 years if you consider the 2 changes of signal. So this one's what we can, the best we have for a time scale is the time scale of this liquid coming up and going down. That is what we call the time scale of granulation, which is associated with the spatial scale, which is associated to the smallest cellule of granulation. Then as you start to consider, and this is a time scale of hours, a little bit shorter than 1 hour. Then as you look at the large scale of things, of these coordinated movements of several granulation cells, it is a time scale of days, 1 to 2 days. And there are people, so the first is called granulation, the second is called supergranulation. And there are people that defend that exists a third intermediary called mesogranulation, that you can see a signature in photometry, but in radial velocity is not as clear. So to answer, sorry, long answer to a direct question. So even though the time scales of these 3 are well defined from first principles, the time scales of granulation are not well defined. And that is the problem that we are going to see after. But it's minutes to days. So pulsations. So during the last 10, 15 years, there was this amazing development in pulsations, and we have people in this institute working on this. There's Christina online. And we learned so much about pulsations. It's amazing. Today, there is an exquisite ability to predict the properties of pulsations from stellar properties. And we can do that. We use the precise stellar characterization to create a pulsation model. And we could predict the pulsation signal to the centimeter per second. And we used Monte Carlo to estimate the effect on the nightly average, the effect that having a pulsation star created on the nightly average. How is this done? You consider the different modes that this star should have, and you consider how these different modes basically creates a radial velocity signal for the times when your detector is integrating. You have to read the detector, integrate again, read the detector, so you have some blind spots when the detector is reading. But you can model all this, and you can predict with a centimeter per second precision what is going to be your pulsation signal. And we could predict it really to the centimeter per second. I was very happy about this. On tau ceti, we can reach a precision, a comparison between the model and the observations agrees to the centimeter per second level, much better than 10 centimeters per second. You can say for sure to the centimeter per second. And on other stars, on other two stars, the other two stars that you saw here in this plot, we need an additional source of noise at the level of 10 centimeters per second, even on one night. So what can this be? It can be the second one, granulation. So granulation is something that is very complex. And it actually represents several mechanisms, as I was saying, the convection of one cell and the convection of a group of cells. And when we look at the radial velocity timescales, you see here the pulsations, and then you start to see the different timescales associated to granulation. But ESPRESSO is not very good to measure this because we don't cover well these timescales of hours to days. What we can do is to try to predict what would be the effect of granulation on our data on the long run and see it's there, if it's there in the end. So if we use the current models of granulation and we try to predict if they are in our data or not, we see that on the night there is we should expect the granulation signal to be of the order of 20 centimeters per second. It's in excess for some stars, but it's still, yeah, it's not great, but we can find arguments to say it's still there. But then on the long run, we should see an effect of 60 centimeters per second, which would make very difficult to detect a planet like our own. Is it there? We're going to check. But if we look at activity as a whole, we can try to understand if our different diagnostics represent well stellar activity. And this is something Piero has been working on. He will show to us one of these days. And something we can do if we don't have a model that reproduces it completely is to try to understand if our lines with enough maximum contrast, the bisector, or the activity indicators are associated with a high degree of correlation with the radial velocity. So this is just a funny diagram in which I represent the correlation coefficient that goes from 0 to the area of noise to 1, if there is a correlation, for the different stars. And we see that on tau ceti, there is basically no correlation. It's very low correlation for all the indicators. Then on this star, there is a detectable correlation on all indicators except for this one, because it's not calibrated for this type of stars, it's for M dwarfs. And then on another M dwarf, we see again no obvious effect of correlation. So this is to represent to you that we still have a lot to learn about activity indicators. We have these things that we call activity, and we have these activity indicators, but we still have a lot to learn and a lot to try on how to inspect the radial velocities. But okay, can we model activity, and can we model in particular this rotation and these long-term timescales I was talking about? Yes, we can use, here I use the Gaussian process, a tool called Kima, developed by Faria, and we could reproduce the rotation of the star and the rotation signature of the star on the radial velocities with an amplitude below the meter per second for tau ceti, comparable to the jitter, and with the properties that are very similar to those we see on the sun. I don't want to bother you with details. That is the gist of it. The most important thing to note is that when we correct for all these activity effects, we can reach a photon noise floor of 40 centimeters per second over 3.5 years. That is the bottom line. And if you look at the scatter around this model during 1 year, it can be as low as 20 to 30 centimeters per second. So, are we there yet? Are we able to detect a planet like our own? Not yet, but we are getting close. And to represent that, here I plotted some the diagram that represents the planetary mass that we are able to detect from our data. And we see here for these 3 stars, we see the planetary mass that we can detect confidently in our data up to the habitable zone that you see represented in blue over there. And you see that for Tau Ceti, the star that we observed most intensively, we reach 1.6 Earth masses at 100 days, but when we go to the habitable zone, it's already at 2. And for other stars, it's for this star that is very active, the one that showed a lot of activity signals here in the middle, it's harder to characterize activity, so we are actually at 1425 Earth masses. That's our limit. But then for some quiet M stars, we can reach 2 to 4 Earth masses with ESPRESSO. So, can we detect a planet like our own? No, not yet, but we are getting there.
But sorry to bother.
Sure.
But how many observations would you need for these planets in the habitable zone?
So here, with Tau Ceti, we currently have something like 100 plus nights.
Okay.
For each night, we observe for roughly 20 minutes to measure these pulsations and to average them out. And for these stars, we have 60 to 80 nights.
Okay.
And now the question is, if we wanted to reduce this to 1.0, we would probably have to double the number of nights on Tau Ceti, HD 10700. But we may double the number of nights, and we may reach another noise floor. We may need to improve the modeling. I cannot guarantee you, no one can guarantee you that with 100 more nights, we would reduce the scatter to half. Okay. Any other question? But what is interesting is that, well, several of these stars have announced planets and we don't find them. For instance, this one has a planet here that is well within our detection ability and we don't see any signal. So we had to say that. And on Tau Ceti on the top, you see also those hexagons. There is one that is sitting way above our detection limit. We didn't see it. We saw this signal that was attributed to another one, which is half of the rotation period. So we don't think that's a planet. But yeah, this is just to illustrate that when you look at the stars and when you look at the stars with activity models, it's very hard to be 100% sure on what's a planet and what's not a planet. So to wrap it up and to represent graphically what we do and what we can't do. So if we look at ESPRESSO GTO and the blind search, we could understand well several phenomena that have an impact on stars and radial velocities. I think pulsations are well understood and modeled at 10 centimeters per second, like we wanted, sometimes even better. Granulation is complicated because we predict a signal of 60 centimeters per second that we don't see. So the question, is it going to be a problem? We don't know. So far, it's not obviously a problem. At 40 centimeters per second is not there. Maybe if we have 100 more observations, maybe we will be a signal of granulation. But I don't expect it to be 40 centimeters per second because that's everything. So granulation can be 30 centimeters per second. But then it's half what the models predict. Questions to answer. Rotational modulation, it actually works well enough. It can be used to characterize activity on a wide range of scenarios. Some stars allow you to characterize activity very well. We saw it on Proxima, we saw it on Tau Ceti. Some others are not as easy to characterize. And it looks like it depends more on the star than on anything else. That's a bit, how to say, uncomfortable. We don't want physics that changes with stars, right? It looks like our models are very simple and they are not good enough for some stars. The model was very good for our quietest star, Tau Ceti, which is actually one of the most quiet stars that we know, much more quiet than the sun. So we are starting to run into a problem of understanding the physics of the stars. And then we use the planetary detection tools like KIMA, among others, and we reach a detectability limit, what we call a compatibility limit, because we calculated it in a slightly different way, of 2 to 4 Earth masses, which is very good. It's not 1 Earth mass, but it's 2 to 4. We could not detect planets like this, but we are getting close, and it's worth continuing. And food for thought and ideas for the next. Of course, the best time to plan an experiment is when you finished, of course. But what can we do now? Okay, with this superpower, which is insight. Okay, I think there are 3 things I would put my money on. The first is to find a physical model for granulation. I think we don't have a physical model for granulation in radial velocity signature. We inherited the granulation model from photometry that was very well understood, and we don't have a good model for granulation. It's just like not so good. I think we should study additional sources of noise below 50 centimeters per second, because maybe these 40 centimeters per second we measure are not the ones that we have been discussing. They can be different things. We saw on this diagram of the sun a lot of things that we have been ignoring, of course, because we don't know how to do flares. These flares are very easy to detect. Some flares are detectable with the naked eye. It's on these images. But you also have low amplitude flares that can have a radial velocity signature. So there are many mechanisms that we did not have to study because we were not at the precision level. Now we are. Now we need to study them. I think flares is one of them. And small flares, called microflares, is going to be one of them in the near future. And I think that a last thing to do is to find more accurate radial velocity models. If possible, more better physically motivated activity models, because the ones that we have are good, but maybe they are the limitation. And that's it. Thank you.
So if you go through your second to last slide, the one just before. So no, the right after that with the knobs.
With the knobs.
Yeah. So if every knob was on the greenest tile, do you think we would still need GP models? Do you think we will one day get rid of them if we have like a good enough understanding of all of the time scale of stellar activity, or it will, in your opinion, always be like enough unknown so that we need them? Maybe we can use them in more like physically motivated models. Like I know Jean-Baptiste Delille has been working on Fennery, which uses GPs, but like in a more physically based. So do you think we can one day get rid of them completely, or is it?
So this, I don't know. Honest answer, I don't know. And then the long answer is these knobs represent the best we can do, and in particular, this knob depends a lot on GPs. Activity of rotational modulation activity is basically corrected with GPs. And we understand the basic physics of it. We understand the physics of a star. We understand the physics of a spot, the evolution timescales of a spot, how a spot disperses, how it's surrounded by plages. I think that is good. I think that is good. It's not perfect. It uses a GP, but it uses physics. When you fit a parameter or you get a posterior, you look at the evolution timescale and you see, this is around 110 days, more or less. very flat. It's like we have on the sun. That's okay. Or you look at the rotational periods and you see 40 days, which is comparable to the rotation of many stars, with an overturn at 20, and you say, okay, that's understandable. My problem is when we cannot even understand these things. Like the granulation, you have these signatures, and it's more noise than anything else, first of all. And then you don't have a good physical reason for the timescales, which is the most basic thing. Let's not even discuss the amplitude. So that's the problem for me. So I think, yeah, maybe in the future we would be able to model everything without the GPs. I think it will be very hard. But our problem is much more fundamental than that. Is really, even if we have a GP, we cannot interpret it well for some mechanisms.
Isabel,
I'm an absolute ignorant. I work on galaxies. Just in case I'm asking something very stupid. In the context of the instrumentation for the extremely large telescope, what's the impact of what you're saying is for all those instruments related with the study?
So yeah, so this observations require a lot of time. As you could see, we were talking about 100 nights of observation for one star. And that doesn't play well with the very large telescopes. Most instruments that are built for the very large telescopes, like Andes for the ELT or Chorus for the GTC even, they are much more oriented towards transits in which you observe one night and you get it or you don't. So in a way, radial velocities and the detection of small planets is not shaping the instrumentation of these telescopes. But ESPRESSO is. This instrument, which became by accident, ESPRESSO became by accident one of the best instruments for atmospheres, is actually the precursor of the other instruments, but not the science case. These other instruments will be very high resolution spectrographs, try to be as stable as possible so that we don't introduce effects on the line shapes. But for instance, they will not have a stability over longer than one night. They will probably be stable over days, but certainly not over months, because that is expensive, that requires calibration, that requires a lot of technical choices that have a cost. And they usually have a cost in photons. Because if you put something to stabilize, you take some photons. You put something to stabilize the light, it takes some photons. So yeah, short answer, it's shaping. The instrumentation is being shaped, but the science case is going into a different direction a little bit.
Thanks, Pedro, for your very talk. I have a couple of questions. One is regarding, you were showing the signal to noise ratio as a function of photons, I think, and then depending on the star. And if I remember correctly, for M star, M star, the noise is much lower, right?
That's correct.
Than for the other star. Is that because the kind of Earth, like the Earth size, let's say, planet should be closer to the star, in the case why this signal noise is smaller, or is another reason?
What you're saying is absolutely correct. The signal of the same planet with the same mass on an M star is smaller. That is correct. So planets are easier to detect around lighter stars. That is true. But here, what we are representing is simply the noise in radial velocity, the formal error in radial velocity as a function of signal to noise. So this is just the formal error on the spectrum. One point represents the spectrum, and the spectrum has a global noise in meters per second that is below the others. As you said, the noise here is smaller. So if it comes from the spectrum, it doesn't depend on the mass, what is it? It's because these stars have a forest of lines. So while here we have 4,000, 5,000 lines on one spectrum, on M dwarfs, we can have 12,000 lines. So even though the lines are shallower, they contribute on the average information on the spectra, actually allows us to reach a better signal or a more precise signal. The problem is that the signal to noise doesn't reach here because they are faint. So the curve is below, but I wish we could have a star, M dwarf with magnitude 5 or 6, like the ones that are asked to reach here. So in a way, it compensates a bit.
Yeah, thank you.
Welcome.
And the second question, sorry, I have to. It's, I'm not sure I understood there was, at the end, a table in which you were showing the results of KIMA, a table,
yeah.
the difference, yeah, that one.
This one, yes.
Yeah, this one. Not the table. Table, what I understand is that, okay, you have 3 stars, you have up to 100 days, and you can detect planets of 2 the Earth mass.
Correct.
With up to, but I don't understand, for 5 days, what is 0.7? So, I mean, I don't understand this.
Thank
I
you.
understand if you observe for 100 days, you can reduce the detection of the mass, kind of.
Yes.
Maybe tell me if I'm saying something very stupid, but why you have 0.7 there?
So let me try to explain it with a different way. So when you have a planet on a wider orbit, the signal of this planet is smaller. The planets on shorter orbits have induce a stronger movement on the star and a stronger radial velocity. As they move further away, the star in radial velocity is moving slower. So these signals, the signal for the same planet on a wider orbit reaches lower velocities. So what we have represented here is the signals that are compatible with the data. So when you have noise, you can reach a much better precision on shorter periods because the planets would introduce something that was above the noise. But as you move the planet further and further away, the signal coming from the planet becomes so small that it's harder to detect. So that's why when you look at these plots, which is the compatibility of planets with the noise, you see something that increases as a function of period. So this is the orbital period. And you see that as you increase the orbital period, you can only detect larger and larger planets.
What you have on the y-axis, sorry, is mass, I can see that.
Planetary mass, and here is,
planetary mass.
and here is period. So what happens is that we can detect very light planets on very short orbits, 0.7 mass. And then as the period increases, we are able to detect smaller and smaller, or lighter and lighter. Sorry. As the period increases, we are able to detect only heavier and heavier planets.
Yeah, they will produce the same thing.
It is
All these things in the table produce exactly the same thing. Yeah, sorry,
I had understood those were the days where you had observed.
Sorry.
No, makes more sense.
Sorry. Maybe I should have said only that. Maybe I should have said only that and not cut the caption. That's a bad idea. Sorry.
Okay. Thank you, Pedro, for this fascinating talk. Although it's not my field of the research, it was very clear to me. My field of research is young star and protoplanetarities. Perhaps this question is outside of the scope of your talk, but could you comment what is so difficult to try to apply the radial velocity methods for the case as young star? I understand that your target are mature stars, but perhaps in the case of young star, we can add some phenomena in addition to pulsation, gradation activity for the accretion process in this early space. Would you say a few words about perhaps the status of the field research? If you know, there is some people working on this.
Yes, there are. I did a bit of it, and it's very difficult because if I had to sum it in one sentence, I would say that the number of stochastic events in radial velocity is much higher than the number of modeled events. So what does this mean? It means that if you look at an M dwarf that is not active, like João Faria looked at, and you look at the activity indicators that are supposed to trace activity, you see something that varies smoothly because it's actually tracking slow varying effects on the star, like the position of the spots. This is actually tracking the rotational period. When you look at very active stars, each point in radial velocity has an error bar just introduced by random events that is much larger. So this creates a very difficult barrier to what we can model because this is stochastic. One could model it on the long run, but we would need dozens and dozens of rotational periods, dozens and dozens of accumulations of the events. While here, we can do it with 2-3 times the rotational period. So this is the main limitation. Still, people are doing it, especially when they don't have the choice. There is TESS that is providing us a lot of interesting candidates. There's Pierre over there. And there are stars that are active and they are candidates. So we are trying to model the best that we can with these advanced models. But the main limitation in one sentence is that there is a high level of stochastic variability that comes from the star that you cannot associate to a well-identified cause like a spot rotating. No, it's something that is very fast for our timescales. It's days. So we cannot model it well, and we are limited. We would have to acquire observations for many years, many more years to reach the same results we reach on quiet stars.
It would be great to detect protoplanets for radial velocity in case of the star, no, but perhaps this complexity very hard to do that.
When I met Alvaro in 2007, we were looking into that already, and it still was not done, or it was only done for some planets that are already old, because basically, when you look at the radial velocities of a star in a protoplanetary phase, the signals are of kilometers per second, just because of activity. So to detect a planet that is 10 times smaller, would need all the corrections. And it's difficult. There is one case of one planet announced on a very young star, and there have been many observations that cannot reproduce the signal. Maybe it's there, maybe it's not. It's hard to say.
Any other question?
So what do you think? So you were talking about other rows under 50 centimeters per second, other effects. How much you think it is affecting right now not doing telluric correction to all of these meshes? Because we will never escape. I mean, unless we do Armstrong space, which not gonna happen at this centimeter per second level, may happen in the future, but not at this level. So how much is the budget that could be associated with telluric correction?
So yeah, we tried to estimate this for ESPRESSO. Simple case: optical, visible, wavelength range. There is oxygen, there is OH, there is water, on basically 3 species, the simplest case we could imagine, and we could see that the telluric correction was reaching a level of the order of 10, 20, sometimes 60 centimeters per second. For ESPRESSO, we actually, the data set that reaches the 40 centimeters per second was telluric corrected because of that. So visible in what is the best condition possible from the nature is already limited by telluric correction. If you go to the near infrared, for sure, it's going to be meters per second. So that is going to be that is currently a limitation. That's a limitation for NIRPs. It is being addressed, but I think it's the reason why reaching the same precision as ESPRESSO on NIRPs, even if the instrument was the same, is very difficult because basically the atmosphere is very different.
I just want to say that with NIRPS, which is in the near infrared with Proxima, we managed to get under the meter per second for the timing correction, but it's very, very fun.
Under the meter per
And
second.
it's going crazy.
So this was forward modeling tellurics
Yes.
based on a few species, and then I
Correct.
guess considering different air mass and whatever.
Yes. It's
So-
very simple. It's so simple. It's deceiving. It's you know the air mass of the observation. You know the distribution of the molecules in the atmosphere. There are only three, so you model the line by line. It's this simple law, Beer-Lambert law, that allows you to basically reproduce the line as a function of optical depth, and it corrects super well. But yeah, but it's very difficult, and it is a showstopper for the infrared as of now, and I think it's gonna probably take the same role as activity plays for other stars, for near infrared stars.
So goes up to 700 nanometer or something like that.
Yeah, but that's peanuts. That's still
Yeah, everybody that is going nowadays to 1 micron, there are a lot of tellurics.
yeah.
Just between 700 and 1 micron.
Yes.
No one is taking, like, if the budget is 20 to 60 centimeters per second, from where there is no tellurics, right, which is below
Yes.
700 nanometer. Like, that budget can approach the 1 meter per second without going to the near infrared. I'm saying all these red optical, like for example, Carmen's and other issues. It's just probably at the order of 1 meter per second. And I don't think our telluric corrections are that good.
No.
Especially to take into account micro tellurics, all these tiny effects.
Yeah, another way of saying that is that another way of saying what you're saying is that people extend the wavelengths of the spectrograph so that you can increase the signal to noise here, right? You can go lower. So you can go down this slope of formal noise, but then you don't get much better than the formal noise because basically there is another thing that gets added on top of the formal noise. But this was the reason why ESPRESSO was cut there. ESPRESSO was cut there because we didn't want that trouble. We could not solve that problem. Other people that look specifically at M dwarfs, like you were saying, like HPF, Marunex, they go into the red because they say they need the photons. They need the photons, and the rest they take care after.
But then they mask tellurics.
And they mask
you're
tellurics.
losing all the lines that you are gaining by going better.
So what they can do better, but they can only do a bit better in the end. But they can do better, but yeah, not that much.
Do we have any question from the people online?
No, there's no question from them.
So then there is nothing else.
Final questions, just.
Short, please.
I would like to know is Proxima C is confirmed?
Yes.
Proxima B, maybe it's well accepted, but I really don't know.
Yes, that is correct. Proxima B 11 days is very confirmed. Proxima C 5 days is confirmed. Proxima C is the one with many years. It's not confirmed. Proxima D at 5 days is confirmed. The problem of Proxima C, the third to be detected, is that it has a time scale that is very long. And as such, it could only be observed with HARPS. And it's very difficult to reach that precision on HARPS because of the plots that you saw here. Because if you can average out, these points are individual points, and they only reveal this shape because you stack them in phase. Because it's only 11 days. This is piled in 11 days. If you do a phase folding of years, you only have a few points. Not to mention that you have to subtract all the other planets, but you only have a few points per orbit. So you cannot reach a good precision on the Proxima C. And you will spend some years until you can.
Yeah,
We should cut. Okay, so we thank Pedro again.
Thank you.
It's not a problem into the bottleneck into the granulation.
For me, the biggest problem now is the granulation.
The data you have shown, yeah,
The data